your code book handy. So the stuff that we went over, which is the water pump as well as the water heater, what I do have for you is now, Matt, we need to know how they work. Really cool when you walk into a house, into a building, knowing how the air handling unit works or how the water heater works is good. But more important than knowing how it works is how to design a electrical power system to install these equipments. Okay, so I would like you guys to draw that one. This is an example number one. I took a 3 horsepower. It's a 3 horsepower, 240 volt. Let's call this one water pump. Water pump. So I have a water pump and given to me as a 3 horsepower, 240 volt. Cool. And I need to size the following. Number one, can you guys see that? I started with my panel. Here's my panel. And here's my pump at the bottom. My panel all the way to my pump. I need to size the branch circuits. This is my branch circuit. The second one is the overcurrent protection device. The third one is the disconnect. The fourth one is called the overload. The fifth one is the controller and the controller. Any comments, guys? Any questions about what we will be required to do for the system? Everybody draw that one. Give you a few seconds here to draw that. One more time. I have a water pump. That's powered electrical water pump. It's given by the manufacturer as 3 horsepower, 240, single phase. And it's powered from a panel. The circuit breaker, I need to size the circuit breaker, the branch circuit, the disconnect, the controller, and the overload in this order. So when you guys have any motor, it doesn't have to be a water pump, it could be a fan. That's what you will be required to provide for the manufacturers to install this system. So I'm going to give you guys a few seconds before I start sizing these systems. Number one is, it's not called the feeder, it's called branch circuits. Branch circuits, yeah. And then what I want to do right next to it, I want to size these systems. I'm going to size them. Any comments, any questions about what we have? Everybody knows what we have? We have the water pump that we were just talking about. And our job is to go based on the NEC code book and size all these equipments. Cool? Let me know when you guys are done with that sketch. So this stuff will be in our next test. Exactly the same information, basically. So, all right. So one more time. So this is my panel. Can you guys see this is my panel? Example number one, my panel. I took a branch circuit, overcurrent protection device, through a branch circuit conductor into a disconnect, into a controller, into an overload. Before we go ahead and start, Matt, I want to review with you the function of each one of them. The main reason why we have a circuit breaker number 2 is what? Short circuit and ground fault protection. The main reason why we have number 1, which is the branch circuit, is these are the interstate highways that's going to transfer the electrical power into the pump so it can work. So the branch circuit. The third one is the disconnect. The disconnect, the main reason for this, having the disconnect is because we want to continue to have 10 fingers in each hand. In both hands. 5 fingers in each hand. 10 fingers total. And we don't want to get electrocuted, right? Safety. Okay, number 5. Why do we have number 5? The controller. Why do we have a controller for a sump pump? Do you really want to go into a water pump and turn it on and off every time you need water, or do you want it to work automatically, right? You want it to work automatically, so we have a controller. So number 5 is a controller. Number 4 is the overload. If this pump is to get overloaded for whatever reason, typically malfunction in these pumps, do you want the pump to burn, or you want the overload to trip to give you an idea, hey, go maintain that pump before it burns, right? That's what the overload is. Any comments, any questions about these 5 very important things that we need to size for any pump? Can I have a thumbs up, Chad? Yeah, we got it? Okay. The first thing, guys, we do, so I want to start with number 1. Number 1. Number one is called, and you guys know that, it's called branch circuit conductors. Branch circuit conductors. I need to size the branch circuit conductors. That's number one, the branch circuit conductors. Before you size the branch circuit conductors, guys, you need to find the following. You need to take the 10 horsepower at 240 volt and find the full load current from table, and I'm going to write tables here, table 430 dot, and I'm going to go directly to this 248. 248. Okay, the most important thing, guys, when we size, can you guys have you noticed that when we size conductors and disconnects, we size it based on amps? For motors, and I assume some of you have never heard of motors, I know two of you guys have done that. For motors, because there's so many motors, the Smarter Than Chad have a section. Can you guys see that? This is the NDC code book article section or table 430.248. Because motors are made by many manufacturers, Matt, and different manufacturers have slightly different full load amps. The Smarter Than Chad decided, what if we list all the common, not all the commonly used motors in one table, and we list the full load current for them, so people like Chad, when they're designing a system, they don't have to go struggle with what the heck is the full load current of this motor, right? Because to find the full load of current of a motor, guys, you need to find the efficiency and the power factor of a motor. How do I know the efficiency of power? I have no idea what the efficiency of the power factor of this motor. So in order to find the full load current, they have tables in the NDC code book. Please highlight this table. This is table 430.248. There's many tables. This is for single phase. This is for two phases. And there's one at the bottom before I go there. They're all the same. This is for the three phase, right? Can you guys see that? So let's go. I assume that you guys have never seen this table. So this is how you read this table. These are very important. This is for single phase, and it goes for ranges of voltages. Can you guys see the ranges of voltages, guys? Right here. So if your voltage between 110 to 220, it covers it. If your voltage between 220 and 240, it covers it. Do you see why? So the voltage that I have is 240. So my 240 is close to what? Is it close to 208, 200, or 115? 230 is closer. So for my 240 voltage, my 240 voltage system, my motors 99% of the time will be rated for 230. Here's what they do for motors, guys. If the system voltage, here's the system voltage. Can you see? The system voltage is 240. By the time you pull the conductors all the way up here, they're still going to lose voltage here, right? They rate the equipment for 230. So they allow you 10 volts to lose them and away, and this equipment is continuing to operate properly. So that's why the system voltage is slightly larger than the equivalent voltage, slightly, not a lot. Okay, so for a 240 volt, we go here, and it was 3 horsepower. Here's my horsepower. Can you guys see that? Here's my horsepower. Here's my voltage, because that's equivalent. 230 is goes with 240. What's the full load current? This is the full load current, 70. That's how you use this table. Can I have thumbs up, Chad? We know how to use this table. Cool? Straightforward. If that was a 10 horsepower, what would the full load current be with this boy? 50. If that was at 1/6 of a horsepower, what would the full voltage would be? 2.2. If the voltage of this was 120, okay, 120. Where would the 120 go? Between 110 to 120, you're going to go right here, 115, right? Closer. So if it was a 3 horsepower, 120, the full load current would be what? 34. This is called full load current from the NDC. Can I have thumbs up, Chad? We know how to do that. Good. So let's take a snapshot of that baby. All right. Okay, so we got a snapshot of this. Now everybody knows where we got the 17, right? We got the 17 right here. Can you guys see that? There's my 17. So let's go directly. Okay, so this will be my 17 amps. Equal, this will be equal 17 amps. Everybody knows where the 17 amps came to be? Okay, good. Then the next, then the NDC code book, guys, motors are continuous load. Motors are continuous load. Then when we size them, when we size the conductors, 1.25 multiplied by 17, because it's continuous load, that will get me at 21.3 amps. And then you take the 21.3 amps, take it to table 310.15 B16. B16, these are branch circuits under 75-degree column because they're motors, and that will give me two conductors number 12 AWG. Two conductors number 12 AWG. Any comments, guys? Any questions? That's the branch circuits for this motors. The branch circuit size of this motor. And I do have a list that gives you all this good stuff, guys. When we go to the commercial, I have a list of the articles and the sections and so forth. For the time being, and this value here for the this 128, let me use this value here, is coming from 430.22. Everybody knows 430. These are the NEC code book 430.22. Okay, so now we sized the conductors. Number 2, we sized the conductors. Why 2 conductors, by the way? Anybody knows why 2 conductors? Why 2 conductors? It's a 240. Do you need a neutral? No, unless they tell you you need a neutral. You don't need a neutral. So 2 conductors. AWG, THHW. Did we say THHW too? THHW. Why do you think we use the THHW? It's a wet location. So we need a THHW. Cool. Any question, guys, about the branch circuit? Now we have 2 conductors. You know? 2 conductors. Now, are you going to put them in a cable or in a conduit? Your choice. That could be an NM cable, number 12 conductor. No, well, it has to be a UF cable in order to get the W in it. A UF cable, 12-2, and you pull that cable underground, bury it, and go all the way to the pump, done. Or it could be a THHW, 2 conductors, and you put them in a conduit, size appropriately. Typically, for this size, you can 2 conductors. The smallest, I can tell you right now, it's ½ an inch. You can't go lower than ½ an inch anyway. So ½ an inch PVC conduit, pull it all the way to the water pump, and put the conductors in it, tie them to the other end. Okay. Number 2, the overcurrent protection device. Overcurrent protection device, and I need to use a circuit breaker. For overcurrent protection devices, guys, there are options. You have to use options. For overcurrent protection devices, you have options. So you can use circuit breakers, or you can use you can use circuit breakers, or you can use fuses. So I'm going to go directly to the NEC code book and go to the table that I would like you guys to highlight. 430.52. Come on, 430.52. Right, there you go. 430.52. If you have not seen this table, please highlight it. This is the table that you use for motors. We're going to be using it for a long, so get used to it, guys. Please highlight this table. That's how we size the overcurrent protection device for any equipment that has a motor. Any equipment that has a motor. Okay, let's see how that table works. I want to bring to your attention, guys, circuit breakers. Here's most of the time you're either in circuit. These are my circuit breakers, inverse type circuit breakers. There are two types of fuses, either non-time delay fuse or dual element time delay fuse. And sometimes you might be with instantaneous trip circuit breakers. I'm not going to talk about that one. So for circuit breakers, for Karen, you have a choice to make. Which type of circuit breakers, which type of overcurrent device you need to use? I want to use inverse type circuit breakers. Ladies and gentlemen, you're looking at the right. These are called inverse type circuit breakers. That's what I want to decide. Okay, for inverse type circuit breakers, the second thing, is it single phase? Is it polyphase, three phase? Is it energy efficient? Can you guys see that? It says energy efficient here. I'm sorry, other than energy efficient, is it energy efficient? Is it synchronous motor? Is it wound rotor motor? Or is it DC? Now, you guys all agree with your friend Chad that we are in the single phase business. So we're right here. Cool? Single phase. We will be using this table all year. So you know it now, you'll check yourself good. Because we're going to be visiting it for a whole year, guys. Okay, we're single phase. Why single phase? I'm telling you, the problem is single phase. All right, okay, now, which one of these four types of overcomputation device would you like to use, Chad? I told you I want circuit breaker. The most common for single phase. Okay, for circuit breaker, what's my multiplier? What's my multiplier for inverse type circuit breakers? Inverse type circuit breaker, 250. Inverse type circuit breaker, 250. And if you read through all this stuff right here, guys, it tells you if it's not a standard, go up. If you read underneath it, it will tell you if it's not a standard circuit breakers for multi. Okay, so if it's not a standard, you are allowed to go up. Okay, everybody, guys, did you guys get these? Everybody got that? Okay, so let me take a snapshot at this, capture, and go to, did we capture it? Okay. Thought we did. Where did it go? I don't think I took a snapshot of it. Okay. One more time before I, okay. Yeah. Capture. There you go. Okay, so now let's go back to my, again, these will be all PDF for you guys. So now you know what we're doing. So let's go back and take the 2.5. Everybody knows why 2.5 times 17. I'm happy to have the answers for these. 2.5 times 17 gets you 42.5 amps. 42.5 amps. Then you want to go to 42.5 amps. You need to take it to 240.6. Okay, let's take it to 240.6, guys. I think I have it here. There you go. 240.6. Here's the 240.6. 240.6. I want to remind you, my math came up to be, I have 42.5 amps. I need to size the circuit breaker. So you're going to go take it to 240.6. Here's 240.6. It says fuses and fixed type circuit breakers. Here's all the sizes that we use in the US. We start from 15 and we go all the way to 4,000, even to 6,000. The most common one up to 4,000. You can have 1, 3, 6, 10 fuses. These are the standard size fuses that we use in the US. Non-adjustable trip circuit breakers right here, guys. Leave this one until the commercial industrial project. We will be using the bottom one, the B, later on. So we're now in the A's. Okay, so if you guys look at 42.5, what's my next standard overcomputation device? I have 42.5. My next standard is what? 45. Can I have thumbs up, Chad? We know how to use this table. A crime against humanity if you guys leave Dunwoody not knowing how to use these tables. Okay, so let's go directly into, so everybody knows now I went to 45 amps. So if it's not a standard, you go up to the next standard. Up to the next standard. Okay? Number three. Number three is disconnect. Disconnect. Why do we need the disconnect mat? Safely isolate the system so we leave 10 fingers and 2 hands. Number one, and also don't get shots. Okay, the disconnect. For the disconnect, guys, I'm not going to take you to the NEC code book. Here's 430.110. Your reference for the disconnect size is 430.110. If you guys go there, it tells you 1.15 times 17. This is 19.55 amps. And if you take the 19.55 amps, you're going to take this one to the wall, page 312. You're going to get 30 amps. Gentlemen, when you say DeWalt, page 3-12, that's I told you. On the test, if you don't have DeWalt for the first 7 weeks, I'm okay. Next, the commercial industrial project, you must have that one. So if you guys have this one, it says sizes of disconnects. Right here, the first disconnect, the smallest disconnect you can buy is 30 amps. Everybody understands what D.W. DeWalt, this book right here in front of you? So my disconnect is going to be 30 amps. So what do? Go call Warner Electric or Vikings or Graybar, order yourself a 30 amp 240 disconnect, throw it on the wall, and wire it. Right? That's what people are going to pay you guys to size this stuff for them. Now all these sizes are you draw this line, you put the size in it, give it to a journeyman or a master, then they should go install it. Tell them what type of wire, EMT conduits we're going to use. Any comments, guys? Any questions about the first three? Should I move next? Okay, so let's go to next. We talked about these. We talked about these. Okay, next, overload. Overload protection. So I want to go to my overload protection. My overload protection. Overload protection. Okay, for overload protection, guys. For overload protection. Huh? I'm sorry, what? 430.3. Okay, you got that one. For overload protection, your article section is 430.32. 430.32. That's where it tells you the following. If you guys go there, it tells you this is how you size it. Unless, and I do have, I have it here. Okay, where did it go? I thought I had it. There you go, right here. 430.32. 430.32, guys, it tells you the default. Can I start with the default, guys? Because that's important. For overload, your default, all other motors, default is 150. Your default is what? 115. Unless one of the following. The service factor is 115 or greater, then you go 125. The temperature rise is 40 or less, then you go 125. Can I get you guys to understand? For overload, the default is 115, 115%. Unless, rule number one, is if the service factor is 115 or larger. Now, what the heck is the service factor? A service factor, guys, SF will be on the motor. This will indicate that the motor can be overloaded for a short period of time, 15%. So if it's a 10 horsepower motor, you can pull 11.5 horsepower out of it for a short amount of time. to accommodate overload condition. Okay? Temperature rise 40 or less. This will tell you that the temperature, the windings have been sized. The temperature, you can go 40 degree. It will not rise more than 40 degree above the ambient temperature. Unless you hear these two, temperature rise and service factor, your default, what's your default? 150. Math, does it make sense? I know some others have seen this before. Does it make? Your job, guys, is to highlight this one and keep it handy for future use. Okay, so we go there. Now, then we need, then this is how it goes. Then you go 1.15 multiplied by, but then the C code book, guys, you need the full load amp, and next to it, name plate. From the nameplate, not the AnySQL book that we guys that I provided for you. The nameplate. Did you guys hear me? Not the nameplate. What's a nameplate? You go to the motor itself and you read. It says that current is this amount. The nameplate. So it's not the 17. It's not 17. Okay, now then I have to give you a disclaimer here. I'm going to tell you that this. What is it? 3 horsepower at 240 full load amp equal 15 amps. This is my nameplate. Nameplate. So I am giving you, I have to give you this information. Right on the nameplate. Then, because I gave you this info, then you can continue. Then you can take 1.15 times 15 equal, you times it by 1.15 times 15, that will get you a healthy 17.2 amps. And that's how you're going to set your overload. There are two types of overloads. One type is a heater, literally heating element. It heats up. It kicks a contact to open. The other side, guys, is electronic. It senses electronically that the current is higher than it's rated for, and it kicks a contact to open. The job of an overload is to interrupt the flow of energy to the motor, stop the flow of energy of the motor. So when you set your overload, you're going to set it at 17.2. Cool? 17.2. We don't go up. If it's not 17.2, you have to go down. If you can't find it, if you can't set it up, adjust it. You go here and you adjust it at 17. There's no 17.2. You have to go to 17. For me, leave it at 17.2 here for the example. Number 5. Number 5 is controller. Controller. For controller, you need to go to 430.83. 430.83 is your controller. Okay? Here's what the controllers are rated for. It will tell you it has to be rated for 3 horsepower at 240 at single phase. That's how you, when you buy a controller for a motor, Karen, you're going to pick up the phone and call Viking and say, hey, I need you to get me a single phase 240 3 horsepower controller. Then what they do is they take you into DeWalt. I want you guys to use DeWalt because they have the controller that in the secret book in this little booklet. If I can find them now, when you want them, you can find them. Okay, horsepower rating for 240 AC switches. There you go. Are we single phase? Single phase. Okay, so for single phase, so DeWalt, if you guys go to page 6-4, that's why I would like you to grab that one we have. At the page is 6-4. Don't forget to go to single phase. If you go to there, and I assume it's going to be 3 horsepower, it's going to be, this will be number 1. the size will be NEMA number one. NEMA number one. NEMA number one, I'm looking at it right here, guys. NEMA number one will get you 3 horsepower. NEMA number one. Any comments, guys? Any questions? So, NEMA number one, you are describing a controller. Everybody knows a controller. You guys haven't been with us 1/4, yeah, right? You haven't done that. A controller is basically 2 contacts. You push a button and close and open it. It's a switch. It's a fancy switch. Okay. Have a coil. Energize the coil. When you energize the coil, it physically, mechanically slams 2 contacts or more shut. You're going to be wiring them later on with Chase. In our motor lab, you're going to get sick of them. You're going to tons of them. But for the time being, when you go there, you understand that NEMA 1. What's a NEMA 1? NEMA 1, NEMA is National Electrical Manufacturer Association. That's how they rate them. NEMA size 1, if you buy a size 1 single phase, it will give you up to 3 horsepower, 240 single phase. The last thing I'm going to do, guys, is for the branch circuit, which is, what was it, number 1. I'm going to go back to number 1, will you? I want to go back to number 1 here. And for the number 1, I'm going to size the equipment grounding conductor. They call it equipment grounding conductor. EGC, equipment grounding conductor. I will size the equipment grounding conductor. Why? Because I'm going to flex. I want to have a flex that goes to this pump or PVC, and I need an equipment ground conductor. 2 hots, fine. That's just to send the power to the equipment. How about I need to ground the frame of the equipment? I need an equipment ground conductor. How do you size this baby? The way you size this baby is based on overcurrent protection device. What's my overcurrent protection device? 45 circuit breaker equal 45 amps. Oops. I don't like it when it does that. That's grounding. Let's get this one here grounded. Now circuit breaker equal 45. You're going to take this one to table 250.122. Okay, this is how they size them, guys. I believe I have the table for you right here. This is table 250. Please, if you have not highlighted this table, please highlight this table. This is how we size the equipment grounding conductor, 250.22. Okay, now remember, I have a 45 circuit breakers. So this the size of the circuit breaker is 45 amps. Can you guys see that? Okay, I can go 13, 15, 30. My next standard is 60. I have to go up. 60 will give me what size? Number 10. 60 will give me size number 10. So what size an equipment ground conductor do I need? One conductor, number 10. A, W, G, T, H, H, W. There's one little problem though. Number 10. There's one little problem. The size of the conductor, the branch circuit conductor, what size the branch circuit conductor is? 12. The equipment grounding conductor is number 10. The code says, guys, the equipment grounding conductor does not need to be larger than the ungrounded conductor. So, if it's, so I know I came up with one conductor number 10. One conductor number 10, right? One conductor number 10, AWG. But the code says, then what you need to do, you need to cross that one, and you don't need to go, and then make it one conductor number 12, AWG. Why? Can you guys see the branch? Here's an example of the motor. I have two pole circuit breakers. The two conductors coming to the motor is number 12. We just sized them. The equivalent ground conductor came up with number 10. The code says if the equivalent grounded conductor is more than the ungrounded conductor, you do not need to go larger, right? So I know my calculation came up with number 10, but I drop it down to number 12 because I shall not need more than number 12. Can I have thumbs up, Chad? This is the most confusing part, even for seniors. So always look at the ungrounded conductor, which is the hot conductors. Had these hot conductors been number 8, do you guys hear me? If that was number 8, then this will continue being number 10. So, long story short, so I don't confuse you more. So this, I'm going to go across this, and I'm going to say the size would be what? One conductor, number what? 12 AWG THHW. Why? Because I do not need to go larger than ungrounded conductor. Any question, guys? Any questions? That's it. So we size 6 things for 5 things for this system, including the equivalent grounded conductor. I do have one shorter example for you for the water pump. Water pump is easy. For the water heater, it's much easier than the motors. 3 things to calculate for it, not 5. 3 things. Am I the only one who is excited? 3 things. Any comments? Any questions, guys? I do have another 2 examples, not for you guys. We'll go over another 2 examples like these, so kind of stick in your head. And we're going to do a couple of examples in the 3-phase when we go to 3-phase. So by the time you graduate from here, this hopefully, if you get it now, you got it. You can build on it. If you did not, you have 3 more chances to get it before you leave. Any comments? Any questions? Summarize, my friends. I sized the overcurrent protection device, the conductor, the disconnect, the controller, the overload for a motor. Done. I can change this one into a 10 horsepower motor and nothing will change. You just change, the numbers will change. The process continues to be the same. Okay, so now, before I move on, guys, any questions? Should I move to the water heater and then we'll, okay? Now remember, this will be PDF'd and on the network for you too. Okay, water heaters. Water heaters. So this is example number 2. It talks about water heater. Can you guys draw this thing for me, please? Take a few seconds to draw. I'll give you a few seconds here. This is a water heater. And the system, my system is, my panel is 240, 120. And I need to size the fuse or the circuit breaker, the conductors, as well as the disconnect for this water heater. So again, this example is for water heater. Okay, water heater. And I need to size, like I said, the following. Example number 2 is a water heater. And we need to size a few things for this water heater. I need, it's a water heater, 500 watt, 5,000 watt, 240. We need the conductor, the disconnect, and the overcurrent protection device. 3 things only. Not a whole lot. Not a whole lot. Okay. Let me know when you guys are ready to go. Roll. The first thing I would like to size is branch circuit conductors. Before we go to the water heater, guys, I want to take you to a table I would like you to highlight. Could you please go to, which page would that be? Go to Article 4. This should be 422. 422. 422. This should be in 422. Article 422, guys, talk about appliances. Water heater is an appliances. If you guys go to 422.e, 422.11e, this is coming from 422.11e. Okay? If you guys go to 422.11e, guys, when you're with your friend Chad, your NDC code book must always be with you. You must always highlight the stuff. You know, that's your Bible. Okay, here's what this says. I don't know if I can erase that one. Okay, I can't erase that. Okay. If you read through this, this is for non-motor appliances. An appliance that does not have a motor in it. Does the water heater has a motor? No, it doesn't have a motor. Okay. So a water heater does not have a motor. So here's what the NDC code book for talk about appliances. It says not to exceed the nameplate in the appliances, the first one, not to exceed 20% if the overcurrent protection rating is not marked and the appliances is 13.3 amps. So if you have a piece of equipment and appliance says 13.3 amps, you cannot exceed 20 amps in it. You put 20 amp circuit. And not to exceed 150% of the appliance's rated current if the overcurrent protection device is more than 113. And if you don't hit the standard, you can go to the next standard. And if you don't hit the standard, you can go to the next standard. One more time. If you guys go through this one, it will tell you the cutoff is the full load amp of the appliances. Is the full load of the amp of the appliances 13.3 amps or less, Adam? Then the overcurrent protection device cannot be smaller than number 20 amps. Circuit breaker. If it's more, then your multiplier is 150%. And if you don't hit the standard, you can't go to the next standard. Can I have thumbs up, Chad? We fully understand that one? Okay. Now let's go apply that one. So that's where the information is coming from. Branch circuits. For my water heater, branch circuits. For my branch circuit, the first thing you need to do is find the I. I equal the 5000 divided by 240. Find the full load current because we size things based on current. That'll give me 20.8 amps. The full load current of this water heater is 20.8 amps. 20.8 amps. 20.8 amps. Okay. For appliances, for 11. Okay. So now for the branch circuits, we got that one. Now for branch circuits, guys, water heaters are continuous load. Water heaters are continuous load. So we're going to take, that's the first step. We're going to take 1.25 because continuous load, multiply it by 208. If you go there, since it's continuous load, we're going to size it. We got this one, give me 26 amps. 26 amps. Okay? Then you take your 26 amps, take it to table 310.15B16 under 60-degree column because it's not a motor. And that will get you two conductors, number 10, AWGTHHN. So that we have two conductors. We're 22. Okay. Electric water heaters, storage water heaters. Okay. So we got that one. Overload branch circuits. Shall not exceed the protected device rated more than appliances. Okay. All right, so we size this one. The second one we need to size, guys, is overload. Number 2 is overcurrent protection device, which is circuit breaker. For the circuit breaker, guys, since you took 1.5, multiply it. Remember that table that we were just looking about, 150%, multiplied by a 20.8. If you take 150 multiplied by 20.8, that will get you 31.2 amps. 31.2 amps. 31.2 amps. Then you take the 31.2 amps, take it to 240.6, and go down, though you can go up to 30 amps. Though you are allowed to go up. So I have my 30 amp circuit breaker protecting the heater, 30 amp circuit breaker. Can number 10 be protected by 30 amps on a heater? Yep. For heater, yep. So here's my overcurrent protection device. 1.5 is right here. Not exceeding 150% of the appliance's rated current if the overcurrent protection device is not marked and the appliance is rated 13.3 amps. That's where the 1.5 came to be. Can you see that? Okay, so I went, even though you can go up, but I went down. Down is safer. The last thing is the disconnect. This disconnect, guys, my disconnect why do we use it? Safety. The disconnect, for disconnect, the way I size it, I say disconnect 1.25, exactly like the overconduction, exactly like the conductors, times a 20.8. That will give me 26 amps. 26 amps. Take it to DeWalt. DeWalt 3-12 will get you a 30 amp 2-pole disconnect. 30 amp 2-pole DeWalt. DW is DeWalt from this book right here. Now, Karen, can I use the circuit breaker as a disconnect? Absolutely. Absolutely. Do I need a disconnect if the water heater is right next to the panel, within 50 feet of the panel? No, you don't need a disconnect. The circuit breaker acts as your disconnect. When do you need it? Why do you guys throw a disconnect for me power-wise, right? You were throwing disconnects all over, right? For your friend Chad. Why? Anybody knows why? Because the water heaters, the panel for the water heaters are not in the same room. They're they're not out of sight. They're out of sight. They're not within sight. So where would you get that conductor here? That multiplier, CSK. You're going to hear the CSK a lot. These are my initials. That's how we would do it. I size it like the conductors. That's how we size the conductor. So you need the disconnect to be able to disconnect the full load current. The full load current is 20.8. The next standard disconnect anyway is 30. So, but I like to use a continuous load, the same like we size a conductor for 1.25. Okay, last thing, I keep saying last thing, is one branch circuit equipment grounding conductor. The same thing, equipment grounding conductor. You're going to take the 30 amps, take it to table 250.122. What would that give you? We just did that one table. Is it number 12? There you go. Here's the table, 30 amps. Is that 30 amps, 15? Is that 20 or 30? 30 amps, number 10. So for 30 amps, then what do you need? Number 10, right? Can you guys see that? For 30 amps. Yeah, for 30 amps, we need number 10. Then my equipment grounding conductor is going to be one conductor, number 10, AWGTHHN. Do I have to lower it? Can you guys see that? Do I have to lower that number 10 to number 12? Do I have to lower the number 10 to number 12? Why? Because the conductors are number 10. The phase conductors, the hot conductors, number 10. Had they been number 12, then you lower it to number 12. Here's your branch circuit. Any comments, guys? Any questions? So we size the branch circuits, conductors and overcurrent protection device, and equipment ground conductor and disconnect. Any comments? Any questions? That's all I have for you. I will go over 2 examples like this as we move on to, just to get it stick. So when you size the water heater for me, and you came up with 30 amp, 2 conductors, number 12, that's how you should have done it. You guys have hot water heater. If you do the calculation for the water heater, you should come up with the same size. Okay, thank you.